is g inverse y, and we divide by this. Let's see, g dx, but this one is same as dg inverse differentiated by y. I don't know the name of the theorem for this, but remember from calculus? So inverse and y. Okay, so after all, we have this formula. So that is from the density of x, we derive the density of y. Okay? Here we assume that the function g is monotone increasing. What if it's monotone decreasing? So instead of this, what if we have something like this? Still, it's monotone, so we still have inverse function, but in this case, we have a negative sign. So f y, we include this negative sign. You should try to find out why this is necessary. Okay. But in this case, this will have values, negative values, because it's decreasing. So after all, with this negative sign, it will be positive. Okay, so we will never have negative values for density function. Okay, we will never have negative values for density function. It's impossible. Okay, in any case, we have so this is monotone decreasing, decreasing g of x. Okay, so when it's increasing function, this is positive sign, but decreasing function is negative sign. So we can actually summarize both cases by using absolute value. Okay, so we just put absolute value. So this includes both increasing and decreasing g. Okay. So here's one example. Let's say we have a uniform random variable which is 1 between 0 and 1. Okay, so this is like 1, so it's 0 and 1. Okay, so x is here like this. Then define a new random variable by x squared. Okay, within this interval between 0 and 1, this is just an increasing function, right? It's monotone increasing function. So we have the inverse function. Obviously, the inverse function is, let's say, if we have y equal to x squared, then x is equal to square root of y, right? So we differentiate it, and we get what? 2 square root of y. So the density function of y should be, so density of x is 1, and the derivative is this. So the density is, after all, we have this. And it should look like y and obviously, if x moves between 0 and 1, y moves between 0 and 1, right? So 0 and 1. And what does it look like? When y is 0, it should explode to infinity. And when y is 1, its square root of y is 1, so it should be 1/2. Okay, so 1/2. So it should stay here. It should look like something like this. So this should be the density of y. Okay. You know, although probability itself cannot be greater than 1, the density, the value of density function can be greater than 1. In fact, in this case, it will be infinity, near 0. Okay. Interesting. Is that true, really? It sounds strange, but well, maybe I'm wrong, so let's check in tutorial. I hope this is right. Okay. So anyway, this is how you change variables. And what else? Okay. Now we have multivariate distribution. Okay. Okay. Now, if we have two random variables at once, x and y. Okay, for example, x is the point of a die, red die, and the point of white die, two dice. Okay, then we may consider joint probability. Probability that x takes the value of this x, and the random variable y takes the value of y. We can consider joint probability. So again, what this really means is the subset of omega such that x of omega takes the value of x and y of omega takes the value of y. Okay? So yeah, so this is the joint probability, and from this we can define a marginal probability. Okay, so if we add all possible values of y, okay, probability of this and this, so we add over all possible values of this y, then we should get the probability of x. Okay. And also, of course, if we sum over all possible values of x, we should have probability of y. Why is this the case? So let's consider the Venn diagram again. So we have, in this case, two random variables. Let's see. Yeah, I think it's easier to consider two separate sets for x and y. So x and y. So this is omega. These are real numbers. Okay. So we take a value of x here and take the inverse image here. Okay. And we take a value y here and take its inverse image here. Now, of course, we are not taking a single point, but we are taking a subset consisting of a single point here. Okay. Then this, this and this means this intersection. Yeah. So what this event means is this intersection. Maybe I should have written bigger. Something like this. So yeah. Yeah, so this intersection corresponds to this joint probability. Okay? This joint probability. So if we take all possible values of y and sum over, okay, so that means we take each point here, and for each point we take the inverse image and add them all. So summing means, each point is disjoint from other points. So we can just take the union of all these sets from inverse images of y. So that will cover entire omega. So after all, what we have is entire omega and x equal to x. So that means just this. Okay, same for the second one. Okay, take this one and take the intersection, take this one, take the intersection, take this one, intersection, and so on. Just continue, and it will cover entire omega. So after all, it's nothing different from just considering the random variable x. Okay. Okay, this is for a discrete random variable. And for continuous random variables, we may define a joint probability density like xy and xy. Okay? But the idea is the same. But in this case, joint probability will be like x1, x2, and y1, y2 will be double integral. Okay. But the idea is the same. Okay. And we can also define conditional probability density. And remember the definition of conditional probability? Probability of, let's say, A given B was defined as the joint probability of A and B divided by probability of B. Okay? So this was the definition. Similarly, we can define conditional probability density. So let's say probability density of x given that y is a certain value. Okay, so this is defined as this joint density divided by the value of density at specified value of y. Okay. Okay, so this is the density of x given that the value of y is fixed. And of course, if the random variables x and y are independent, that means the probability that this is oh, in discrete case, if this joint probability can be split into two parts, which contain only x and the other contain only y, then they are disjoint, right? And similar for continuous random variables. So in case of continuous random variables, if x and y are independent in this sense, then we can split the density function into two parts. Sorry, this is not y, this is x. Okay, independent. So in other words, if you can show that the joint distribution, joint density can be actually expressed as a product of two densities, then they are independent. Okay. Remember the definition of independence in the previous lecture? In that case, it was defined in terms of this joint probability. Okay. So this x is this value and y is this value. Is this really joint probability? So this means actually this event and this event, right? Of course, this event means this omega such that x is x, and similar for y, right? So I think, yeah. So this means, remember the definition of intersection? This is exactly intersection between this event and this event, right? So it's basically the same thing. Okay. I think that's all for today. Any questions?